Everyone. This is Ablah AlAmri, a PhD student at the University of Sheffield. Today, I'm going to present our study, which is about the impact of wireless channel error on the visual quality of learning-based image coding. This work is supervised by Dr. Charith Abhayaratne. So first, I would like to start by going back on the history to briefly talk about the evolution of mobile network generation. And maybe some of us remember like the first generation of the mobile network generation in 1980, when they produced it at the first time. And at that time, it has allowed us to use the analog voice communication to produce voice call. And at that time, it just 2.4 kilobytes per second, which had a low capacity, low security, and poor voice quality. Then 10 years later, they produced the second generation which introduced the digital voice communication, offer us a better call quality. And also the new thing at that time is the SMS messages. Then later, 10 years later, in 2000, they produced the new one, which is third generation with a high data rate, enable a mobile internet and multimedia, also a video call and web browsing. Then in 2010, the fourth generation has come out with a high-speed mobile broadband, enable the HD streaming video. Then in 2018, the 5G is push this speed further with much faster speed and low latency, massive device connectivity which is support the Internet of Things, self-driving vehicle, remote surgery, and produce a new type of application such as virtual reality, augmented reality. And maybe some of us now using the 5G and 4G. However, within the few years in 2020, we promised to have the 6G, which aims for even a higher data rate, intelligent communication, enable advanced applications such as the 3D video call, and we can see the healthcare through the internet, maybe the robot doing some surgery, and some surgery may be doing with distance. And this generation, the 6G, aims to integrate everything, space, air, ground, and sea together. However, all of us may be using the social media now, and millions of people sending and receiving multimedia all the time. With this, we may have a massive amount of data that need to process, store, and transfer. To enable to store this data, the huge data of transfer, we need an efficient compression or coding to reducing the bandwidth usage, storage, and the latency. For this, I'm focusing now on the image compression pipeline. However, the pipeline itself for compression for A data have the similar general framework, but I'm just focusing in the image compression. The classical image compression framework is essentially having this architecture in general. So if we have input image, then we encode it using source encoding. In the classical way, we may use the cosine Fourier transform as it's used in JPEG, or the wave the wave as used in JPEG 2000, and then use the entropy encoder to convert this data into bit stream. Then adding a channel coder, then sending this data through the channel, and at the receiver side, the channel decoder are applied first to get back this bit stream, then decoding using the source decoding, the classical one, to reconstruct the imaging. However, now some of us may heard about the neural network, the deep learning, and the AI, which is now we use it in our lives. So it is used in the framework and it enhances the framework. And as you can see here in the B framework, which is AI-based image compression framework, where we replaced the old encoder with AI-based encoder and following the same steps. And at the decoder side, they used the inverse AI-based decoder to reconstruct the image. So the main difference between the classical image compression framework and the AI-based image framework is the source encoding that used. In the old one, they used the classical encoder, and in the AI, they used the AI based encoder for encoder and decoder. And recently, the JPEG AI introduced a new learning-based image coding framework. At the transmitter, it has the same architecture as before. The new thing is at the receiver side, it could be applied a fully standard decoding image following exactly the same as the AI framework image-based compression. And the new thing is at the receiver side, they may be just decoding the channel to get back the bit stream, then decoding the entropy. They only apply the entropy decoding. They didn't apply the full AI-based decoder. They just apply the entropy encoder to get back the latent representation, as you see here. And then based on this latent representation, they perform some image processing task or maybe perform computer vision task. And this framework support the machine and human prescriptive. If we do the fully standard decoding image, this is for human prescriptive because the human need to see the image. And if it is for the machine, we don't need to do the fully decoded. We can directly work on the latent representation. Then with this, the wireless communication system has also improved. In the traditional communication system, they used the source encoder, then the channel coder, and so on. In the source decoder, in the traditional communication system, we can use the classical as JPEG or JPEG 2000, or we can use the AI-based and follow the same structure for the traditional communication system. What's new in the communication system? We have a new communication system. It's called semantic communication system. The new part is this one, semantic coding, which is replaced the old source coding with a semantic coding. In this one, they didn't send everything. They just take the input image, then the apply semantic coding, and they only send the semantic feature of this image. And then at the decoder side, used a shared database for this shared database between the transmitter and the receiver. They used this database to get back the reconstructor image. For example, if it is coding this image, then this sky has some details like cloud here, and the semantic, it just code that this part is a sky. then maybe in the decoding side, using the shared database, which is said this is sky, and maybe that the fine details of the sky may be different in the reconstructed image. And then later, in like 3 years, like they introduced a new wireless communication system. It's called joint source channel coding. They combine the source coding and the channel coding together. And if we have input image, then we apply the neural network or the deep learning on this image to get the coding. Then we get the latent representation. They didn't convert it to bit stream. They send this latent representation directly through the channel. And then at the receiver side, they decode this latent representation to get back the image. So the main difference is that they combine the source coding and the channel coding into one component. And they also remove the converting into bit stream. They work directly on the latent representation. The AI-based image compression method, initially when started of using the neural network in the image compression, they try just to change a few blocks with the neural network. In other words, they replaced some part of the main framework with the neural network or use it for specific reason. For example, they may use it just for source encoding and decoding, or maybe or some author use it just for prediction, some pixel at the decoder side. If there is some missing pixel or block, they try to use the neural network to predict the missing pixel. The rest of the framework is following the standard entropy encoder, or maybe used the Humph encoding as in GPG, or the arithmetic coder as in GPG 2000. So the main framework as the standard just replace a few blocks with the neural network. However, the new part, which is based on the neural network, are trainable parts. We can train it to predict or train it to upsample or downsample the image, but the entropy encoder and arithmetic coder are not trainable. So we can't use the full advantage of the neural network for fully end-to-end optimization to reduce the losses of the pixel. So to fix this, the GPG organization has been working on a new standard. It's called GPG AI. This one is completely based on AI, from input to output, to produce the compact latent representation, then converted back to the to reconstructed image. Example of this, or the standard itself is not released yet, but it will release by end of this year. So example of this, or some methods or model that follow the same structure, which is fully based on end-to-end training, like the factorized prior, which is introduced a variation autoencoder that assumed the element of the latent variable are independent. And this assumption, it is fully end-to-end training, but this assumption limited the compression. So in the new one, the scale hyper prior, they produced a side information, which is use a separate learning related space to predict the scale or the variance of this latent but they assume that it is zero mean. Then in the context model and hyperprior network method, they predict both the variance and the mean of this latent presentation, which is make it more accurate, and the output was much better. Now let's a quick recap that for the general framework, we have input image, then we used AI-based coder to get a bit stream, and we sent these bit streams through that channel. Now, if we add a new component, like a new AI-based image coder, which is a new component based on the deep learning to this framework, and we actually don't know what is effect of this on these bit stream. In other words, we can send this bit stream through the channel, and the channel could have some error or noise, and that may affect the bit stream, and we can get a corrupted bit stream. But the corrupted could be from the channel itself, or could be from the new part, which is the neural network part. Then this output or the reconstructed image may have the original image with the noise. So we have some, maybe, we don't know, to the best of our knowledge, there is no study studying this problem, or what is effect of the channel error on the bit stream that comes out from the neural network. So it could be like just color shifting, or priori, or board noise, or maybe some blocks are losses, or maybe the fine details of the texture may be changed a little bit, or maybe just a pixel losses. So to fill this gap, we set up an experimental model, which include an encoder and a channel coding module, followed by a channel simulation module. We used WAG in channel. The main reason is we want to study the effect of channel error on the visual quality of an AI-based image coding. Then we first study the rate distortion for all methods. We used 3 methods with the GPG as a reference, and then we send it through the channel with different SNR level to see the different effect of this level. And we get deeper inside the reason for this effect. As I mentioned, we use the traditional communication system in this experiment because it fits with the method, the AI method that we used, because the other one, they didn't convert it to bit stream, while the method that we study converted to the bit stream. So we use the traditional communication system. We run the simulation with different SNR value from 2 dB to 16 dB. And then we calculate the PSNR and the multi-scale structural similarity. In this study, we used the whole data set of codec data set, the 24 images from this data set, and we ran the experiment through all these data set, and then at the end we calculate the average of the PSNR and the similarity metrics. The method that we used in this study, we used the three different model that is available from Compress AI. The first one with no side information, which is the factorized entropy model. The second one, which is used the mean as a side information, which is the hyperprior with zero mean, and the last one, which is scale hyperprior with non-zero mean, and predict also the variance. All these methods are optimized for mean square error and available in compressed AI. In our experiment, we test for two channel condition: the clean, with there is no error in the channel, and the noisy transmission condition. Now, this is the output from when applied for the codec dataset. We can see the first one is the reference, which is the JPEG. We can see the blue line is the clean, which is the rate distortion for the JPEG. And we can see that with different SNR level, we can see the performance is gradually enhanced when enhance the channel itself. While in the factorize, we can see the orange one is the clean one with assumption of no error, and we can see here when the NSR is 16, it is exactly match the clean line. In other words, we found that when there is no error, when it is reached 16 and above, the result are matching the rate distortion. When it is 14, we can see that there is a difference between the clean and the 14 one. When the quality is low, we can see it is a little bit, but when increasing the quality, you can see there is like 5 dB is the difference. However, when it is less than 14, you can see it is the result are bad. We can see here that all of them like under 10 dB. And the same result for the scale hyperprior with the side information. We got similar result. And when it is under 14, it is less 15 dB. And the last one was MPD 2000 with the mean. It is enhanced a little bit when the dB is 12, and when it is less than, it is above, let's say 13 dB, where we can see here it is almost 10 dB. And for the similarity, we got a similar result. We can see here it is gradually enhanced with enhancing the channel, whereas the rest of the AI-based method, when there is any error on the channel or it is less than 14, the result was bad. Now, let's see the output from this experiment. Now, we can see in the first two lines, they are completely corrupted. The output are completely corrupted. With NSR from 2 to SNR 4 for different quality factor. And when the third one, which is the model that used the mean and the variance, we can see there are a lot of pixel losses we can see here, and the blurry, and we can see some artifact of the color as here. The last line is the JPG, which is the standard. I'm not sure if you can see it, but when at SNR is low, you can see there is a pixel losses. When enhancing the SNR, it is a little bit enhanced. And here is when SNR is 6 to SNR 10, we still have the first two are completely corrupted. The third one still has some blurry artifact and pixel and blocks losses, and the JPG are continue to enhance a little bit with enhancing the channel. And when the NSR is 12, we can see here at the factorize just partially if the image are corrupted and the rest of the image is fine. This is because the end of the entropy encoder may be corrupted. The error position is not at the beginning of the entropy encoder, maybe at the end of the bit stream. That way it is only affect this part, where if the error happen in the beginning or the middle of the entropy encoder, it is completely corrupted the image. And we can see here above the 14 SNR, the image are completely fine. You can see in the second row here, when this is used the side information, that's why you can see it is a little bit worse than the first one, because the corruption could be also happen in the side information, and that make the result a little bit worse. The third one is still have some blurry block clouds and some color artifact, and we can see here that once it's reached 14, the result are fine. And for the last one, the JPG are continue increasing its performance gradually. Now, when we investigate of this, why it is happen, why when there is any error in the entropy encoder, it is completely corrupted, we found that all these methods in compress AI use a range asymmetric numeral system as a range as entropy encoder, and this one is very sensitive to any error. If any error happen in this bit stream, that the error propagation make the whole bit stream are corrupted, whereas the JPG shows a smoother and gradual enhancement in the reconstructor equality when the channel condition improve. And the opposite of JPG, it is come from it uses independent block, then encoded these each independent block, and this localized the error in a specific region. That's why we can see some pixel losses, but not corrupted the whole bit stream. Also, the JPG used fixed a simple statistical assumption, whereas the AI used a learning-based statistical assumption. At the end, we can see that AI code sets I factorize or hyperscale prior or the hyperscale with mean and variance significantly outperform the JPG in terms of compression in a clean channel condition. But if any error happen, if when sending this channel through, sending this bit stream through the channel, the error propagation make a huge effect or make the whole image to be corruption. Now, in the future work, since we now know what happened in this bit stream, we have to focus on improving the error resilient for AI-based model, especially for application in a noisy channel. Also, we need to develop advanced error concealment mechanism that can reduce the visual effect of the bit stream corruption during the decoding. We also have to produce a new mechanism that restrict the error propagation and minimize its effect by using maybe block-based architecture or chunk the bit stream itself, or maybe develop a more robust entropy encoder method that use the locally and globally context modeling, because context modeling can help enhance or it'll help predict the missing pixel. But when using the context modeling, it is slow down the whole operation. So we need a new one, a fast one to control this error propagation and limit its effect. And also during the training, the AI model, we need to add a new, like train it with noise, train it with different noises that may happen during the transmission to make it learn how to conceal this error if it is happen during sending or receiving this bit stream. And thank you. And if you have any question, please ask.